All right, it's 9:40. We'll go ahead and get started. We have a lot to cover and 30 minutes to do it. So this is high-performance JavaScript with Rust. My name is Amir Yasin. In JavaScript terms, I've been writing software since before the beginning of time and done all kinds of crazy things. And now Rust and JavaScript is one of them. Currently work at a company called 2U, which is a pretty cool ed tech company. Shameless plug, we're hiring. If you're interested, find me after the talk and we can chat. So what I hope you get out of this talk is that you get a basic understanding of Rust and enough to take advantage of the performance boost and kind of how to use it, an understanding of how to call Rust from Node, an understanding of when it's worth using Rust and when it's not going to be advantageous to you. What you're not going to get out of this talk is you're not going to become a Rust expert in 30 minutes. That's not a thing. If you want to be an expert, it takes time, but you'll have enough to use it competently and definitely have resources to learn more. So let's get started. What is Rust? Rust is a low-level systems programming language with high-level convenience. So what does that mean? That means it's strongly typed. Everything in Rust, you have to either declare the type or use type inference to get it. It does provide type inference, as I mentioned. You do get some high-level language convenience. So unlike C, you don't have to declare everything. Rust's compiler will try to figure out what a type is. If it can't figure it out, then obviously you'll have to specify it. It's sponsored by Mozilla. It was originally created for the Firefox HTML stuff to help render it faster and more securely and things like that. It has since been used in many, many places, including the world's largest package manager, NPM. They use it for a lot of things. Coursera, Dropbox, just a couple of examples of places where it's currently used. It's designed for speed and safety. Speed is great. Safety is even more amazing. Thing that Rust does. Rust's actual motto is actually hack without fear. So hacking without fear basically means that I can do all kinds of crazy things and the compiler will stop me before I do something that's going to cause me all kinds of problems, or try to anyway. So speed, so AKA why you're here. Rust is a compiled language, which means that it has its own tool chain and spits out a binary at the end. For that reason, it's not necessarily appropriate for modules that you're going to distribute, because obviously if you distribute Rust, then they have to install the Rust toolchain, but for internal modules and things like that, it's a great choice. Rust has no garbage collection or automated resource management. This makes it very predictable. It makes it very fast. You don't pause for GC cycles at random times and things of that nature. You can get very close to the hardware in the sense that you're on the CPU already, but you can also do things like run on the GPU and do all kinds of crazy things with hardware that obviously you can't do with JavaScript. In most cases, Rust is as fast as C, which is extremely impressive. In cases where it's not, it's a pretty close second. And so safety. So the safety is actually a pretty unique feature. You can't have null pointers in Rust where you've freed something and then you try to use it, or you try to use it before it's assigned. Like you kind of get in JavaScript occasionally, you'll get can't call blah 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 of undefined. You'll never see that in Rust. In fact, there's no null at all. There's no such thing as null in Rust. There's no manual memory management. So one thing you might think, if there's no GC, well, now I have to handle my own freeze and my own allocs and things of that nature. But that's not actually true. So what Rust does is it has this very interesting ownership model where the compiler handles all of the freeing and allocating of memory for you without you having to worry about it, but it's all done at compile time, so it keeps it very, very fast. And we'll talk about that ownership model in a minute. The threading is much, much easier because a lot of the problems with threading are thinking about how to manage shared memory. Rust makes that very easy with its model by eliminating data races. If you're not familiar with what a data race is, it's basically when you have two threads running and one thread modifies data, the other thread doesn't realize that, and all hell breaks loose. Those types of bugs are really hard to find, and Rust just eliminates them altogether. So there's even a paper recently that was published where they used Rust's macro system to prevent security leaks by marking things as secret. And then if at any point that secret variable was copied into a space that wasn't marked secret, the compiler would prevent you from even compiling the code. So what is ownership? Ownership is the right to destroy. It's kind of the best way to think about it. If I own a car, I can put that car in a crusher, right? If I loan you that car and you put it in a crusher, we're going to have a problem. So the idea is that one piece, the memory is owned. I can hand out copies, but it's mine to destroy. There can be only one owner of memory. At no point can you have two people owning the same piece of memory, which prevents the data race. So variables are immutable by default, which means that helps the compiler decide, what I can do with this variable. I can mark something as mutable, but by default it's going to be immutable. I can loan you the variable, like I can loan you my car, right? You can look at it, you can do things, you can't really do things to it, but you can do things with it. I can also mark variables as immutable, as I mentioned, and that lets me change the variable once it's set previously, but I can also send out borrows that are mutable, but only one mutable borrow is allowed. Again, we're worried about data races, so you can only have one alterable copy, and if there's an alterable copy out there, no other copies are allowed. So, and that again, to prevent data races and things of that nature. You can transfer ownership to someone else. I can sell you my car. Once I sell you my car, I can't crush it anymore. You are now the owner of it. You can do whatever you want with it. I can borrow it. I can mutably borrow it, but I don't any longer have the right to destroy it. A little bit more about memory. Because of this memory model, you can ensure that memory can't be corrupted. The only way to corrupt memory really is to use the unsafe keyword, so you can kind of escape this whole process. So you can interact with some C libraries and things of that nature, but in general, if you're writing in Rust, you won't have any problems with memory. No runtime overhead, and you get the same memory safety as a garbage collected language. It's pretty nice. So enough about memory, and we're here to learn about Rust. So the easiest way to do this is kind of a Rosetta Stone way, and we'll take a look at some JavaScript, and we'll take a look at the equivalent Rust and understand kind of how to transform them. So let's start with functions. So here's a very simple hello world function in JavaScript, and then here's the equivalent Rust version. So in Rust, fn is how you declare a function. Rust has a linter built into the compiler, which will complain at you if you don't kind of do things the Rust way, which is snake casing your variables and your function names and things of that nature. You can turn that off, but it's kind of nice to have consistent looking code. Every function returns a variable or returns a value. Remember, there's no undefined or null. In this case, this function will return an empty tuple. We'll talk about what tuples are in a minute. So variables in JavaScript, here are 3 ways to declare a variable in JavaScript, a couple of ES6 ways, and then the normal way. Here's how we do it in Rust. So let is the only keyword to declare a variable. The first one is immutable. We can never change that x. The second one, we can change that x to whatever we want anytime later. We can't change the type of it, though. So if we try to do 22.0, it's going to complain and say, hey, x1 is an integer. If we want to do that, then we can declare it like y, where we give it a type specification, which comes after the variable, and we'll tell it, hey, this is a float 64, even though it looks like an integer. So flow control. So JavaScript has an if statement, right? So we have if this, if X, do this, else do that. We also have a ternary, which lets us be a little more terse if we don't have a whole lot of stuff, because typing is the hard part of writing software, I guess. So in Rust, we still have the if, but ifs are expressions. So Rust is an expression-based language, so almost everything is an expression. Almost everything can return something or does return something. In this case, if you look at the second one, it's the equivalent of our ternary. If we don't put a semicolon at the end, that last line is what will be returned. So in this case, it's setting X to, or G to 1 or 2 based on the value of X. Flow control in JavaScript, we have switch statements. In Rust, we have match statements. Matches are a little more powerful than switch statements. We can do a little more checking. After we have the one or something, we can do a little bit more analysis before it picks this. You can read about that in the Rust book, but for this purpose, I didn't really write that up. The default is the underscore, and that'll match everything. Oops, too far. So looping in JavaScript, we have while, do, and for. Very similar in Rust. We don't have a do while in Rust. We only have the while loop. We have for with the, but for isn't it's not a counter. It's more of a collection. Like I'm going to take one of each. In this case, if we want to do a count, we can use a range, and a range is defined by in this way. We have 0.10, so it'll do 0 through 9. And then if we have a normal collection, we can just grab thing from the collection and do something with it. And then loop is kind of a shorthand for while true. So types in JavaScript. Yeah. Rust, again, is strongly typed. It has all the standard types, booleans, integers, floats, unsigned, signed. It also has arrays and strings as native types. Arrays and strings are fixed in length. Unlike JavaScript, you can't push or strip from an array or anything like that. A slice is a view into a string or an array. So that's how you kind of get a part of it, and you can operate on part of it. A tuple is, the best way to think of a tuple is a typed fixed length array. So I can say this is an array of an int 64, a float 32, and a string. And so that kind of tells, and you can access those very much the same way you would, like if it's .0, .1, .2 to view into the tuple. But it basically gives you a way to say this is a group of variables that's fixed in this way. Vectors and hash maps are kind of how you push and pop from an array. A hash map is very much like a JavaScript object. So packaging, yarn, obviously, NPM, other things. Rust has cargo. Cargo toml and cargo lock are very much the same as package JSON. In Rust, we use, not import or require. So let's solve a problem, and we'll get into kind of how to use Rust to do this. So given two large numbers, let's find the least common factor of those numbers. So the world's easiest toolchain to install, all you have to do is go to ruststub.rs and click through the steps. It's a pretty nice install experience. Once you have it installed, you can go into a directory and type cargo new and give it a name. Cargo will generate all of the assets for you that you need to get started. By default, this will create a library. Libraries are hard to debug, so it's useful to sometimes create an app and then remove that little app wrapper once you're happy with your code. In order to make this a library that we can load into JavaScript, we want to use a dynamic library rather than a statically linked library that's default created. So we'll add these couple of lines to our cargo toml. So let's go over to the JavaScript side, write some JavaScript code, and then we'll see how it differs. So the first thing we want to do to prepare our JavaScript side is install the FFI. Rust can work with other ways that you link up JavaScript and external languages, but FFI is convenient, easy, nice to use, and that's what we'll use today. So here's the JavaScript version of an LCF function. Takes two numbers, it figures out where to stop, and then it loops through and checks each one to see if they have a common factor, returns the one that, if it finds one, otherwise it returns 0. Here's the equivalent Rust version. So one thing you'll notice is if we remove the compiler directive, they're actually the exact same length. That compiler directive, #nomangle, is a compiler directive that tells the compiler, don't change the name of this function. By default, Rust can rename functions and things of that nature for its own purposes. We don't want that to happen because we're going to bind to this function by name. That first line looks a little scary. Let's go over that. So pub extern, pub means this is a public function. By default, things in Rust are private. Again, safety first. So we have to declare that this is going to be externally accessible from our module. That's what pub does. Extern is a keyword that means use a C call stack. It's a bit technical, but basically it's how things are laid out on the stack, how return values are returned, and how parameters are pushed and things of that nature. And this says we're gonna commonly agree that we're gonna use the C standard. FN LCF, again, this is how we declare a function. In functions, when you pass variables in, there's no type inference. You have, because Rust can't tell, like how, you have to tell it what the variable is going to be. The arrow there is how you specify the return type. So we're going to use int64s. Remember our ternary from the previous one. This is the ternary equivalent, which is let's stop equal the if. And then remember, notice there's no semicolons at the end of those braces, and that lets Rust know, hey, return this value, and then we'll store it in the stop. Again, we don't have the the let check. We just have for check in I to stop. We will check each variable with a modulus, return the check, or return 0. Again, notice that we can return early with the return keyword, or we just have the 0 by itself as the last line with no semicolon, so that'll be returned if it gets to that point. So now that we've written our Rust code, we will compile it. So we use cargo again, and we'll build, and we need to build a release version. So once we're done with that, we should have in our target release folder a lib that we can then link into JavaScript. So now let's connect the two. So here we require our FFI. Ref is a library that gives us types in JavaScript. It lets us marshal these types back and forth. So we'll declare an int64, which we'll get out of ref types, and then we'll we'll tell the FFI library where our native code is and what functions we want to pull out. So it's function name, and then it's kind of backwards. It's return type, then parameters. Or it feels backward to me. I don't know if it feels backward to you. So we have our return type, and then we specify an array of our parameters. And then we can just use it just like a normal function. So you'll notice that console log just calls it as if it was a normal JavaScript module. So let's make this a little more complicated. Let's add some threading to it and add a callback. So this looks a lot scarier, but I promise it's not that much worse. So we need to add these 3 libraries so that we can create threads and move variables around. We need a callback function, so we'll add that to our Rust code here, and this just declares that, hey, we have another C function that will take an int64 when you're done. Arc is atomic reference counting. It lets us share this across threads. So remember I talked about there can be only one owner. So Arc is going to take ownership of our thing and let us see it, and it will manage changing it so that we can share it across threads but still only have one owner. Anytime you see an exclamation point after a function, that's a macro. And macros are really powerful in Rust. I'm not really going to talk about them in depth here, but you can read about them. Vec is a macro that creates a vector given an array. We're just giving this an empty array so that we can get an empty vector. And notice we declared it mutable so that we can push things onto it. If we didn't declare it mutable, we'd be stuck with an empty array that we couldn't do anything with, not particularly useful. So as we move along, we will clone the arc variable that we have and put it in a local variable that we're going to give to the thread. So thread spawn is how we create a thread. That double pipe is not a Boolean, it's a closure. So the move keyword in front of it means move ownership of this thread LCF that I have in the closure to the thread. So if I tried to use this after I declared the thread, I'd get a compile error saying, hey, this variable was moved to this other thread, you can't access it anymore. So once I have that, I'll just call my least common factor function from that thread, and we'll take a look at that function in a second. And then later I'll join the threads. Join basically says, wait for this thread to finish, then call me. I don't care what it returns because my variable is stored in the clone thing that we made. And then once it's done, I'm going to call the load function that the LCF provided with the value. Ordering relaxed means that, or the done function rather. Ordering relaxed means I don't care what order this happens in. In Rust, you specify in the thread on a shared variable like this what order to resolve conflicts. Relaxed means I don't care. And the reason I don't care is that I've only got one thread that's ever going to write to it, and if another thread reads it after it's already written, it's going to cost me one loop, which doesn't matter. So single-threaded LCF, let's take a look at this one. So the additional parameters here are basically the start point and the step size. Because I have multiple threads running, I want to have a stride where I kind of move along. The start is kind of like, okay, I want to start at number 1, 2, 3, whatever, right? However many threads I have. And then the LCF is that reference counted variable that I share across my threads. Really, the only two lines of substance that are different are this LCF store and load, and that's how you access that shared variable. So if I find one, then I'm going to store it. And then I'm going to continue. If I load it and I find that somebody else has already found it, I'm going to return. If I do a store and then an immediate load, I'm going to find that I found it and I'm going to quit. There's no return here. Notice there's no like final 0 because this variable was initialized at 0. If nobody finds it, nobody's going to store anything and it's just going to stay 0. So now calling both versions. So we will add our entry here. You'll notice I did something a little different in the MTLCF. I provided strings for the types. That's another way that you can specify the type. It'll use ref internally. So if you don't want to, have the safety of the variable, if you don't care about that as much, of the variable name, so you don't end up with a typo, you can use this manner of finding the types for convenience. The callback we write, we have to tell the FFI that we have a callback. We have to provide that callback in the FFI wrapper, and then we can just call it exactly like we would a normal Rust method that takes a callback, or sorry, a normal JavaScript method that takes a callback. So how fast is fast? So I did some tests on my laptop, and this is kind of the results that I found. For slow.js, I wrapped it in a try-catch to prevent the compiler from optimizing the code. So it's 9.2 times faster for the multi-threaded Rust versus the slow JavaScript. If you do the single-threaded Rust versus the optimized JavaScript, because we're running multiple times, it'll get optimized pretty quickly, and it's 2.1 times faster even there. If you do the multi-threaded, where I gave it 4 CPUs, or 4 cores rather, it's 7.3 times faster. If you gave it more cores and obviously larger numbers, it would go even faster. But that's kind of the long and the short of the speed boost. So when should you use Rust? So if you need to do things that are heavily computational, like finding so there's a reason that I picked, I don't know if you guys can see that in the back, these very large numbers. These are the sums of primes in the millions. And the reason I did that is so that it would spend some time looking for them. Or the products of primes in the millions. So again, when you need to do something heavily computational, if you need access to hardware like the GPU, it's a good choice. Also, if you want predictable performance, and that's critical, you can't have it pausing on a GC cycle or something like that. Rust is actually a pretty good choice for that. A predictable memory footprint, again, no GC cycle means that it's not going to build up and then tear down and build up and tear down. What's the downside of it? FFI isn't cheap. So if you're adding 2 numbers together, FFI is going to be significantly slower than just doing it in JavaScript. There are faster options like a C++ bridge, which you can write, or Neon, but they're much harder to use. So you're always trading kind of complexity for speed. Passing complex data structures can get a little hairy, so you want to avoid it for that. If possible, make your data structure simple. Having code in 2 languages is inherently more complex than having just JavaScript. You have to have Rust expertise on your team, so that again makes it a little bit more difficult. So if you're interested in learning more, which I hope you are, here's a short list of resources to get you started. All of the code and the slides for this talk are available on my GitHub. Rust by Example is an amazing resource to learn Rust. It's got exercises and things like that you can follow along with. The Node FFI tutorial is a really good place to learn more about FFI if you're interested in that, and if you're actually going to use it, I strongly suggest taking a look at it. Neon bindings are great for higher performance, and if you need to construct JavaScript objects in the Rust, Neon is a great way to go. It's more complex, obviously, than the FFI, but obviously more powerful. Also, I'm Yasin again on Twitter and all the other things, in case you haven't had enough of me. That's my talk, and if you guys have questions, I think we have 47 seconds. So debugging the Rust modules in JavaScript is very difficult. What I would normally do is I would normally create an app and debug it that way using the Rust debugger. And then once you're satisfied with it, then build the lib. 25 seconds. All right, cool. Thank you very much. I hope you guys learned something.